Okay, question 2 from the Level 3 2014 Waves paper. Question 2 is interference. The diagram shows a series of speakers connected together and to a frequency generator producing a single frequency. The speakers act like a diffraction grating. So this is a little bit of a different application of the diffraction grating situation. Many point sources essentially. If we scroll down to question A, the sound wave source is producing a note of wavelength 0.600 metres, so that's 60 centimetres if you put it in your mind in a way that makes nice sense. So 60 centimetres. The distance between the speakers, in fact we should write that down as our wavelength. The distance between the speakers in the line is 35 metres. That's shown there in the diagram, and that's our L measurement if you're considering the formulas. When a person walks along the line AB, so along the line AB down here, the distance between two loud positions is 7.40 metres. That's going to be our X value. Oops, that's going to be our X value, I bumped something. And that's for N equaling 1. So that's the distance between two loud positions. We can take it from any of these individual positions to the next loud position, and that's our X value. Calculate the separation of the speakers D. That's our question mark. So then taking all of that, putting it together, simple calculation, we need to decide what formula we're going to use. There are two formulas that typically work for interference. We just have to decide whether the small angle approximation fits. So theta in this case is going to be much larger than, this doesn't work anyway. Did I get that around the right way? It might be around that way. Anyway, small angle approximation doesn't work. So sine theta does not approximately equal to theta. And we're in that case going to have to use n lambda equals d sine theta. We are trying to calculate the separation of the speakers D, so that's our question mark. We don't know theta, we know n, we know lambda. Now we can calculate theta from a triangle. This is a bit of a trig here. We've got our distance L is 35 metres. We've got our distance X of 7.40 metres. That's 35.0 because significant figures are all important here. So we can then calculate our angle theta from that triangle. And that's what we do, calculate theta from the triangle, plug it into that equation and rearrange for D, and you'll get D from that. So I'm not going to go through that. You can work through the details in your own time. B, explain how the path difference of the waves causes positions of constructive and destructive interference along the line AB. So this actually sounds like a level 2 question. Remember, the path difference is the difference in path from, say, 2 point sources to one of the bright fringes if it's light, or the loud points if it's there. So the path difference will be about that length there, that small length. The path difference is going to be a certain number of wavelengths. So PD as a, not P times D, but PD as a, yeah. And if you are, if your path difference increases, then your wavelength obviously can't change, but you're going to increase the position of the constructive or destructive interference. It's not asking specifically about where it moves along the line and how far along the line it moves, but asking how that path difference causes constructive and destructive. So the level 2 aspect is that when you have a whole number, that is n being 0, 1, 2, 3, so forth, whole numbers of wavelengths path difference, you're going to get constructive. And when you've got basically at plus half a wavelength to each of those positions, you're going to get destructive. Okay, maybe I should use some more colours rather than just doing it that way. And you can go through and give all the details as well. Constructive is where crest meets crest or trough meets trough, and they produce amplitudes of twice the amplitude of a single wave, or that's if you've got 2-point sources, or bright fringe if you've got more than 2 points constructively interfering. Destructive is where a crest meets a trough, and you can work through the rest of that. That's the direction the question's going in. C, explain the effect on the interference pattern of reducing the distance between the speakers. So this is the distance D, and if we go D sine theta equals n lambda, and we consider it from an equation point of view, if we're reducing the distance between the speakers, and it's the effect on the interference pattern, we are not able to change the wavelength. We're not able to change the number of the order, so if we just consider the first order anyway, what's going to happen to that? So to decrease that and get the same n lambda, we have to increase the sine theta component. So increase in sine theta means that theta is also going to increase. So you're going to get wider. Remember, there's your triangle from before. That's theta, that's the source of the speakers, and this is your fringes or your interference points. That's going to stretch out, so it's going to be wider spacing. And it's all centred around that formula again. Okay, D, which is actually the last question, I believe. The frequency generator is now set so that several different frequencies are emitted by each speaker. So it's not just a single frequency. In the light equivalent, it's not monochromatic light. It would be like white light or a mixture. So explain how the sound heard by someone, remember it's sound though it's not light, how the sound heard by someone walking along AB would differ from that described in part B. So part B was single frequency, and now we're considering many frequencies played at the same time. So crucial thing, single frequency, you just have the standard fringe spacing all the way through with, if this is n equals 0, you've got a 1 and a 1 and a 2 and a 2 further down that way, and they're all going to be the same frequency. With many frequencies playing, you're going to get at your central position, at your n equals 0, you're going to get all of those frequencies being played, but at every position further out, the further out you go, you're going to, in fact, every position further out, you're going to get a spectrum of frequencies. If it was light, white light, you would separate out the frequencies like a prism does in a similar way, and you would, from n lambda equals d sine theta again, because d is the same, n is the same, you would expect for a higher wavelength, you would have a higher sine theta and a higher theta. So you're going to have higher wavelength further away, and the lower wavelengths, which corresponds to the higher frequencies, closer. So your F is going to be higher that way. Okay, you hear my voice if you don't read my writing. I think that covers it. Now, this is a comparison, so take all that information and compare it really carefully to the single F situation. And I think that's the end of the question. Let's have a quick look down. Yep, that's the end of it.